Hi everyone, and we are now going to be talking about the Coulomb force, and that is the electric force, and that's the force that is responsible for attraction and repulsion between like charges and unlike charges. If you haven't done the reading, please go ahead and do so. Whoops, that's kind of strange. If you are in Physics 111 or 121, please do the readings in Coletta. Okay. And if you're in Physics 112 and you're using OpenStax, please do Chapter 18. And if you're in Physics 131, please do Chapter 7 in OpenStax Volume 2. Right? Please go ahead and begin your homeworks. Okay? So if you're doing sapling homeworks, begin starting on the first and second homework assignments. All right? And it's going to be really pertinent to what we're doing today. All right. So let's just get to it. Well, the Coulomb's law is this. So Coulomb basically measured this force, and it's a force, and he made a quantitative relationship between the charges of one object and the charges of another object. Okay, so I'm going to mark up this document. Again, to mark up a PDF in Adobe Reader, you're going to go to the comments, and then once that pops out, then you're going to close it. And then these tools will be available to you. And I like to use the pencil tool. Okay. So suppose you had two like charged objects. And this is object 1. It's got an excess charge. And this is object 2 that has an excess charge built up on it. Well, will those charges be attracted or repelled from each other? Okay. Well, if they're like charges, they're going to be repelled. And we're going to do our force diagram on Q1. So if Q1 is being repelled, and this is they're just sitting on the ground and we're looking down on them, then Q1 is going to have a force pushing it to the left. And this is called the Coulomb force. So I always put it F sub Q. And I'm actually going to note the direction on here as well. So that is the vector force diagram of this. Okay. Well, now we've got our force diagram complete. And so what this is saying is this: you have an object that has an excess charge of Q1 on it that is responsible for that repulsive force, but you also have this other object. If that has an extra amount of charge on it, it's going to actually be repelling a lot stronger. And it's going to have this extra force built up on it as well. And what we had learned in the last chapter is that more charges means more repulsive force, but also if we had let me try to see if I have our balloon thing still loaded up. Notice that when I move the balloon and it's really far away, that those electrons over here, which are repelled away from the electrons in the balloon, aren't really reactive. So that tells me that if I bring it closer and then I move them now, notice that they're very reactive. So that means distance is important too. And what they found out was the closer you are, the greater the amount of repulsion or repulsive or attractive force of these two objects. Okay? So Q1 and Q2 are directly proportional. The amount of charge on either or both of these guys is directly proportional to the force, because we're comparing numerator to numerator. And also, the further away you are, so if this distance is really large, then this force is going to become much smaller. In fact, this force is going to be reduced by the square of the distance apart. So distance is important. It's inversely proportional, right? Again, if you look back at this, if I was really far away, not reactive, so not a lot of force. The closer I am, a greater amount of force, right? So that means distance is inversely proportional to force, since we're comparing a numerator to a denominator, okay? What they also found out by graphing force, what they did is they graphed force, and they used a pith ball. There's an experiment that we do in our class for this. So we graphed force versus Q1, Q2 over R squared. When we graphed that, there was this, actually there was a straight line that would come out of this, okay? Okay. Actually, no, though it was, there was this right here, there was a slope, and that slope is K. And K is this constant that drops out, and it's called the electrostatic constant. And it's basically, it doesn't change, and it's 8.99 times 10 to the 9th newtons per meter squared over Coulomb squared. And again, since we're talking about a force, this force is going to be in newtons. And charge, again, charge is going to be in coulombs. And a proton has a positive 1.602 times 10 to the negative 19th coulombs. An electron has negative 1.602 times 10 to the negative 19th. But a lot of times, we're going to be talking about an object that has an excess amount of charge on it, and that will be numbers of electrons built up on an object. So what you would do to find that total number of electrons is divide the total excess charge by a single electron's charge, and then that would be the number of electrons that are built up on that object. Okay? And again, like charges are repulsive, unlike charges are attractive. So when we're going to, you notice I made a little bit of a force diagram. So since we're dealing with forces, and this is electric forces, you're going to have to do force diagrams. So what you're going to do, excuse me, is you're going to be using Coulomb's law. And again, that is K, Q1, Q2 over R squared. And again, since this is a vector, the charge of those Q's aren't going to matter, so you're going to want to put an absolute value around those. Okay? So it's the charge, it's the direction of the force vector is responsible for this being a positive or negative force, not the charge. Charge does not affect a vector. Okay? So the first thing that you're going to want to do when you're doing these is you're going to want to draw a force diagram on the objects. Okay? And you're going to pick one of these objects to do a force diagram on. And the last time I chose this one, again, this time I could choose to do this one. So I would be doing a force diagram on Q2 over here instead of doing it on Q1. Either way, it doesn't matter because forces are always equal and opposite, right? So if Q1 is pushing on Q2, then Q2 has to push back on Q1 in an equal and opposite direction, since this is the force of their mutual repulsion or mutual attraction. Okay? So forces are always equal and opposite. And so if you start, so that's one thing about force diagrams, is that they're always equal and opposite. Okay? But what's important too is that if you start to add just charges just to one of these, well, that's going to cause, so if you add 2 to this is going to, now you're going to double the amount of force that they're repelling on each other. And then if I add 2 to this over here, now I'm going to quadruple the amount of force that they're working on each other, right? So since these Q's are directly proportional to F, the more Q's you add to one or the other or both, the more repulsive or attractive that force is going to be. All right? And again, distance is inversely proportional to the force. The closer you are, the greater the force. The further away, the weaker the Coulomb force. Okay, so it's a non-contact forces, and non-contact forces, you have to keep in mind the distance between objects, and usually non-contact forces like gravitational forces drop off by 1 over r squared, or 1 over the distance between the planets or the two charged objects squared. Okay, and as a reminder again, this is going to get ground into you, but this is the electrostatic constant, and it is 8.99 times 10 to the 9th newtons per meter squared per Newton meter squared per Coulomb squared. Okay? So let's talk about the Coulomb force. Okay? So if you have two positives, okay, if you have two positives working on each other, and this is just a positive, just one positive Q, and I'll just put like a little positive 1Q and another positive 1Q, okay, they're going to be repelling each other, again, with an equal and opposite force. And that is this force right here. Again, you put absolute values around the charges because that isn't responsible for the direction of the force diagram. What's responsible is whether they're attracted or repelled, okay? So if you, this is a positive 1Q, positive 1Q, okay? If you have negative Q's, they're also going to be repulsive. I should put a negative 1Q and a negative 1Q2. So if both these are just single electrons, they're going to be repelling as well, okay? And again, those forces will be equal and opposite. If you have a negative 1Q and a positive 1Q, well, they're going to be attracted now, okay? And so that force diagram is now going to be reversed, and you now have to think about the direction of the force vector, whether they're attracted or repelling, and that's going to be responsible for this being a positive or negative force, okay? But let's talk about, in more in depth, the relationship of Q's to force in this illustrated context, and also distance to force. Suppose you just had a positive 1Q here and a positive 1Q here. So you have just two little protons, okay? All right, well, suppose they're both have a repulsive force of 1F on each of them, okay? 1F to the left, that force vector is to the left. This 1F is to the right, and so that'll be a positive force vector. This will be a negative force vector because the direction of the force vector, okay? Well, what if this distance between these positive 1Qs were now doubled, right? Now they're 2r apart. So now this is a distance 2r apart. Well, now that force is going to drop off by the square of that. So if you've increased that distance 2r, that's going to become 4r squared. And that means this force is going to drop off now by 1/4 of the amount. So it's going to get very weak very quickly due to distance. So distance really affects force. It affects force by the square of the distance, right? Very powerful. Now, not to say that charge doesn't affect force as much, but if you had only, so we double the distance here, and it dropped the force off by 1/4, okay? And this is going to be a negative 1/4 because it's pointing to the left. This will be a positive 1/4 because it's pointing to the right. So if we go back to this now, and they're now 1Q and 1Q separated by a distance r. Well, suppose you added another positive here. Well, now you're going to have a positive 2Q. Well, if you put a positive 2Q here, that's only going to double the force. So that is going to now be a negative 2F to the right, and this is going to be a 2F to the left, and this is going to be a positive 2F to the right. So it's only going to double the force, right? In order to quadruple it, you would have to add another Q to the other side or here, and that would actually double the force on it. I mean, quadruple the force on it. So distance is really going to affect it by the square of itself. Okay, it's not directly, it's not perfectly inversely proportional. It's got that square of that inverse that you have to really think about when you're answering questions, conceptual questions about the nature of that Coulomb force. Okay? Okay, well, let's try this now. You have two positively charged particles that are held a distance 4d apart while you measure the repulsion force between them to be F1, just a force, one force, a force to be F1. Well, now you bring those two positively charged objects really close to each other. And now they're only 1D apart, as in right here. And you measure that repulsive force to be F2. What I want you to do is think about which force is going to be greater, F1 where they're further distance apart, or F2 where they're a close distance apart. So what I want you to do is pause the video and I want you to put greater than, equal to, or less than in this relationship. Will F1 be greater than, less than, or equal to F2? Pause the video now and try it out, and also explain the reason why. All right, we're back. Well, I'm asking you a question about that Coulomb force, so I'm going to go ahead and draw it right here. That force is going to be K, which is the electrostatic constant, which is 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. Okay, that's that electrostatic constant. And then we have Q1, and I'm going to call this guy Q1, and I'm also going to draw this guy to be Q1. And then I'm going to put Q2 also in an absolute value, and this is going to be Q2, and this is Q2. But let's say both of those have the same charge on it. Q1 is equal to Q2, which is equal to Q. So they're both equal in charge. And this is over distance squared. Okay. Well, for this part up here, this is going to be, that force F1 is going to be equal to K, Q1, which is just going to be Q, and then Q2, which is also just going to be a Q, right? I said they're equal in charge, all over 4D, that is squared. Well, F1 is going to then just be, I'm going to take the letters, I'm going to multiply them together, that'll be KQ squared, right? Q times Q is going to be Q squared over 16D squared, which I'm going to bring the numbers to the front. That's going to be 1/16 of KQ squared over D squared. And that's equal to F1. So F1 is going to be 1/16 of a KQ squared over D squared. Well, F2, I'm going to do that math down here. I don't like how squished this math looks. This F2 guy right here is also going to be K times Q all over 1D that you've squared, which is now going to just be KQ squared over D squared. So that's just 1 KQ squared over D squared, while F1 is 1/16 KQ squared over D squared. So which is bigger, 1/16 or 1? Well, F2 has to be bigger than F1 because it is 1, and F1 is going to be 1/16. So F2 is greater than F1. All right. So those are the type of conceptual questions that you're going to have to answer in the end of chapter problems. Let's go ahead and do another one. Now you've got two charged objects. All right, one's a positive one's a positive 1Q and the other one's a positive Q, and that is F1. Okay, and you have F2, which is a positive 3Q compared to a positive 1Q, and they're both the same distance apart. Which force is going to be greater now, F1 or F2? Talk to it, try it out and see what you can, and please try to use that Coulomb's force to help explain your reasoning. Pause the video now. All right, well, this case, this is a positive 1Q and this is a positive 1Q, so that Coulomb force is going to be, and we're talking about F1 here, that is going to be K times positive 1Q plus, times a positive 1Q all over 4D that we're going to be squaring. So that is going to be, again, that's going to be 1/16 KQ squared over D squared. and that is going to be F1. F2 is going to be K, and this is a positive 3Q, and this other one is a positive 1Q, and they're also going to be over 4D that you're squaring. Don't put, by the way, I just want to be careful. You're not doing 4D squared. That's 4D squared is not equal to 4D that you're squaring. Okay, just so any distance they give you, put it in brackets and then square what's in that parentheses. So this is actually going to become 3Q times 1Q is going to be 3Q times K. So that'll be 3KQ squared over 16D squared, or that'll be 1/8. Is that 1/8? Oh, let's see. Hold on. What is? Sorry, I'm kind of having a weird moment right now. 16 divided by 3 is geez. Let's do 3 divided by 16. That's 0.18. So that's actually, you can't really reduce it. So that's just going to be 3/16 of a KQ squared over D squared. So 3/16 is greater than 1/16. So again, F2 is going to be 3 times the size of F1. Okay, and that's because this 3Q is directly proportional to that. So the Q's are directly proportional to force, while again, distance is inversely proportional to force, and it's the square of that. Okay. So those are the types of conceptual questions that you're going to be asked in the end of activity quiz. Let's try another one. So you have sphere B, which has 2 times the mass and 3 times the net electric force, electric charge than A. With what acceleration will sphere A move away from sphere B? So will sphere will it be 3 will be 3 times B's acceleration? So will the sphere A have 3 times the B's acceleration? Will it be twice B's acceleration? Will it be the same acceleration, half the acceleration, or 1/3 the acceleration? So what will the acceleration of A be compared to B? So the A sphere be compared to the B sphere. Well, we're going to have to do a force diagram to answer this question. Okay? So sphere A is going to be repelled away from sphere B, and those two forces are going to be equal and opposite. Okay? And I'm going to call this force, this is just a force Q, and it's going to be to the left, and this is also going to be the Coulomb force, and it'll be to the right. But sphere A is going to be accelerating to the right, and sphere B is going to be accelerating to the left. Okay? And I'm going to call this B, and this is going to be acceleration A. Right? Although the forces are equal and opposite, you want to denote A and B for the accelerations. All right? So let's go ahead and let's sum the forces on A over here. So I'm going to sum the x direction forces on A, and that is going to be equal to the Coulomb force to the left, which is then going to also be equal to the mass of A times its acceleration at A. Conversely, over here, I'm going to sum the forces on B, and that is going to be equal to the positive Coulomb force. It's going to have a Coulomb force to the right, and it'll be equal to this other force. But that'll make, this is accelerating to the left, and this is accelerating to the right. That arrow's pointing to the right. So this will be a positive mass of B times the acceleration of B. Okay. Let's do the Coulomb force. That is going to be negative K times, I'm going to put our 3Q here due to our first object, positive 3Q, and our second object has positive 9Q on it, all over, let me try to write that a little bit more legibly. That is going to be a positive 3Q times positive 9Q, which is on object B, all over their distance apart, and I'm just call this a distance D apart. So that'll be a distance D that I'm going to be squaring, and that's equal to its mass. Mass A is just an m, and it's accelerating to the left. Okay? So if I solve for this, I'm going to, the negatives are going to cancel out. I'm going to divide both sides by this negative m. So this top part is going to just become 3 times 9, which is going to be 27 kq squared over d squared, and this is going to be equal to the mass of A, which is just m. So I multiply the negatives out, which is equal to just m times the acceleration of A. So this is going to be 27 kq squared over md squared, and that's the acceleration of A. All right. All right, that is an equation. It's 27 kq squared over md squared, and that's the acceleration of A. Let's do the acceleration of B here, okay? Well, it's going to have the same force on it, but it'll just be to the right, and it'll be, I'm going to put the 9q in front, because I like to put whatever object we're doing the charge on, I like to do that charge first. And the other object is causing the force on it. And again, they're over a distance d apart. And that's going to be equal to the mass of B, which is actually 2m, and it's got an acceleration of B. Okay? I got the 9 and 3 by counting those charges. Okay? Well, this is going to again be K times, that'll be 27 kq squared over d squared is going to be equal to 2m times its acceleration. Divide both sides by 2m, and I'm going to get 27 kq squared over 2d squared. Is that, and I should put 2md squared, which is going to be the acceleration of B. So basically the acceleration of B is going to be, so if I'm going to bring this 2 out in front, so this is going to be 1/2, and I'm going to put 27 kq squared over md squared, which this is the acceleration of B, which then is going to actually, if A is 27 kq squared over md squared, then B's acceleration is going to be half of A's acceleration. So the answer is half, A is going to have twice of B's acceleration, and B is going to have half of A's acceleration. That's what that's saying. So sometimes they're going to be varying both the charge and the mass. Okay? So you have to pay attention to all three of those examples that we just went through. So essentially the problem solving strategy is this. What you're going to do is identify the point charges that can be modeled. So you can identify the charges that can be modeled, and you're going to model them as point charges, just infinitesimally small pieces of space. And then you're going to draw a picture just like we did. And then you're going to draw a force diagram just like we did. Okay? And then you're going to go ahead and then you're going to represent the repulsive and attractive forces as a Coulomb force. Okay, so you have to think about, are these two charges attracting or repelling? Are they like charges or unlike charges? And then you're going to have to label those force vectors. Okay, and then when you go ahead and sum the forces on those, you're going to then have to use the Coulomb's law. So when you apply Newton's second law, okay, you're going to then have to go ahead and sum the forces and then use K, Q1, Q2 over R squared. Don't forget, this is actually the distance apart that you're squaring. So try to remember to put parentheses around the distance apart of those guys. And also remember that the Q's have absolute values on them. It's only the magnitudes of the charges that contribute to the sizes of the forces. The direction of the forces is, you're just going to have to think about that. Are they attractive or repelling? Okay? So let's try this out. Here you've got four cases. You have two charges that are equal in charge. You have a positive Q here and a positive Q here that are distance r apart. Here you've got, in part B, you've got a positive 2Q here and a positive Q over here, and they're 2r apart. Here you've got a positive 2Q here and a positive Q here, and they're a distance r apart. And here you've got a positive Q here and a positive Q here, and they're a distance 2r apart. What I want you to do is do a force diagram on each one of these and calculate the repulsion force between the red Q and the gray Q, and actually have a number for each one of these. But you're going to be doing the force diagrams on the red Qs. So please pause the video now and try this out. Okay? Okay, so again, you're supposed to do a force diagram, and in this particular problem, we want to know what the overall force is on the red charge Q. So you're only going to do force diagrams on this. Okay? Well, let's do the first one. And I'm going to say the first one, the first red charge, since they're both positives, they're going to be repelling each other. So the red charge is going to have a force to the right of this amount. And I'm going to label that the Coulomb force, which is F sub Q. And since that arrow is pointed to the right, that vector is going to be pointing to the right. Okay? All right. Well, there are no other forces acting on the red charge because we're only looking at the Coulomb force in these problems. So now we're going to sum the forces in the x direction on this red charge, on this red charge, and it's got the Coulomb force, and that's equal to its mass times its acceleration. Okay. Now, here we go. Let's go ahead and evaluate that Coulomb force. That is going to be equal, well, the positive I'm going to carry in front, and I'm actually just going to put the absolute value around the entire set of numbers, not just the Q's. So I'm going to do a little change here. I'm going to put the absolute values around the entire Coulomb equation. So that's going to be K, and then you have the red charge, which is its Q, and it's a positive Q. And then you have the gray charge, and here's its positive Q. And you're going to divide that by their distance apart, and their distance apart is R that we're squaring. So I made, even though it's just R, I'm still putting the brackets around. And that's equal to its mass times its acceleration. Okay, so this is going to end up working out to be KQ squared, and I've brought them outside of the absolute value, over R squared. And so that's what the size of this force is. This force is KQ squared over R squared. And we're going to use those variables much like we would use units. Okay? So that's kind of what you're going to do. So if you haven't finished this problem, please do B, C, and D right now. Okay? Pause the video if you have a chance. Okay. Well, let's estimate the sizes of B, C, and D. Well, let's compare A to C first. Okay, so it looks like all we're doing in C is doubling the amount of Q. And on this earlier problem, when we doubled or tripled the Q here, it tripled the force. So I'm thinking by doubling only one of the Q, we're only going to double the force. So I'm going to say this force is going to be twice the size of A's force. So again, this is going to be a positive Q, all right? And I'm estimating that this is going to be twice the size of A's force. B, I'm thinking B, this is kind of hard because you're doubling the Q here, which is going to double the force, but then you're doubling the distance, which is going to drop the force off by a fourth. So I'm guessing this force is going to only be half of B's force, of A's force. So this is going to be half the size of this one. D, you haven't doubled the charges or anything, so they're the same charge, but you've doubled the distance. So I'm assuming that this is going to be about a fourth the size of that. Okay. Well, let's do B. Let's do B together. All right, and then we'll just check my answers on the other two. B, here we go, is going to be F positive Q, and that charge is pointed to the right, and then you set it equal to mass times acceleration by applying Newton's second law. That is going to yield, I'm going to bring this positive because the force vector is pointed to the right out in front, and that's equal to K times 2Q times Q. Okay, actually I should have reversed those. I want to do my red charge first, and then the charge that's causing my force second. So the gray charge was 2Q, so I'm putting that second. And now their distance is 2r apart, and you're squaring that. And that's equal to mass times acceleration. Well, that mass times acceleration, I'm going to then multiply this all out. That's going to be 2kq squared over 4r squared. And that is exactly what I imagined. That is 1/2 kq squared over r squared. So the B force, the force B, is actually going to be 1/2 of the original force. Well, if you haven't tried C and D, please do so now. Okay, I've put the answers on the next slide. So this first force is kq squared over r squared. This next force is 1/2 kq squared over r squared. Since this force right here, you've just doubled that charge, which is then just going to double the force because they're directly proportional to each other. And then in D, you doubled the distance, and since that distance is being squared, that force is dropped off by a fourth. Okay, so it is exactly what I've imagined. So there you go. And I've tried to draw those vectors proportional to the estimated sizes. Okay, how did you do? Well, what's worse than one clown showing up to your birthday party? 2 clowns. Well, here we're going to do the same problem now, except now we have we're going to have a negative Q and then a positive Q. And not only that, we're going to have them separated by distances of D's. And then you're going to have to get the overall force on the red charge due to the negative Q, and then the overall force on the red charge due to the positive Q, and then add those together. Okay, so you're going to actually be drawing 2 force vectors on our positive red Q due to the other charges here. Okay? Well, let's do it. This negative Q is really close to our positive Q here, so it's going to have a large force, and it's going to be attractive. So is going to cause a force to the left that is going to be large, and that's due to the negative q acting on our positive q. And since that vector's to the left, that negative goes in front. And I'm just denoting what's causing the force on our red q by this negative q. Well, this positive q is really far away, and it would be repulsive, but it's only going to have a small force, and so it's a positive q acting on our q, and is pointed to the right, so that's why it has a positive there. Okay. Well, now let's estimate that force. Let's sum the forces in the x direction. Okay, and that's equal to, I'm just going to copy what I see over here. I got an F negative q. Again, this negative q has nothing to do with F, with this negative. It's just the fact that this vector is pointed to the left. Plus F positive q pointed to the right, and that's equal to mass times acceleration. Okay, well, now we're going to apply the Coulomb's force. That negative q, I'm going to do this, k, and our red charge is a positive q, and that other charge is a negative q, and it's a distance d away squared. So that's this force. Now let's do the other force. That is going to be plus k times our red q, and that other q, that gray q, is also a positive q, and it's a distance 2d away squared in the absolute value. So I'm just going to absolute value the whole equation. It just makes it easier. All right. Well, this equation is going to be negative k times q is going to be kq squared, and this is d that you're squaring, so that's going to be d squared, plus this is k times positive q over 2d squared, so that's going to be kq squared over 4d squared, and that's equal to mass times acceleration. All right. So this is a negative 1, and this is a fourth, so I'm going to pull this kq squared over d squared out, and we're going to have a negative 1 plus a fourth equals ma. So you just pull that kq squared over d squared out, and you get a negative 1 plus a fourth. All right? Well, negative 1 plus a fourth is actually going to be kq squared over d squared is going to actually be negative 3/4, which is then just going to be negative 3/4 kq squared over d squared equals mass times acceleration. So this force is going to, and overall going to yield a net force to the left of negative 3/4. Negative is the direction is pointed, kq squared over d squared. Okay, so that's what you're supposed to do in these problems. You're supposed to go ahead and you're going to have to create two forces on our red q, and there are two Coulomb forces acting on our red q in one dimension. Okay, so what I want you to do is I want you to try B, and let's see, I want you to do B, C, and D, and then what I want you to do is I want you to check your answers on the next page. Okay, so please try those out, and then after you've completed them, move on to the next page and we'll see how you do. Okay, well, on the next page I've drawn the force diagrams on each one of these. Okay, and I've actually even labeled the forces here for you. Okay, and then I've summed the forces and I've given you those charges. Okay, notice C is being pushed, this red charge is being pushed to the left greatly by this middle charge, and then a little bit weakly by this other charge. And so that's going to result in a negative kq squared over r squared, which is due to this guy, plus a negative kq squared over 2r that you're going to square, which is going to be 4r squared. And so that's going to be negative 1 minus a fourth, which is going to end up being negative 5/4 kq squared over r squared. So you're supposed to draw those vectors and sum the forces on each one of these red charges, and then get an overall answer in the form of kq squared over r squared. Okay? How did you do? Hopefully you did well. Well, another type of problem they typically do is this. And it's always formulated in, so this is another type of problem that they do where they kind of formulate it in a very strange way. So let's suppose you have two positive charges. You have a positive Q charge here and a positive Q charge here, and both these positive Q's are anchored in place. Okay. Now, you're going to take a positive charge that has, you're going to take a positive 2Q charge and you're going to place it somewhere on this number line such that it will not move. Now this positive 2Q charge is free to move, but you're going to want to place it such that it will not move. So that means the forces on this are going to be balanced. Okay? So where do you think you would place this positive 2Q on this number line such that it will not move? And again, these two red charges are anchored in place. So they're not going to be able to move. So this positive 2Q charge that is free to move, you need to put it in a place where it's not going to move. Where do you think it's going to be placed closest to? 1, 2, 3, 4, or 5. Okay. Well, like I said, you want to place it on the number line where the forces are balanced on it. Okay. So if you have to do these little if then statements, right? So if you place a positive 2Q here, right here, well, this positive Q is going to push it really far to the left, and this positive Q is going to push it weakly to the left. So this object is just going to take off and accelerate to the left. The antithesis is true for this. If you place a positive 2Q over here, this Q right there, just closest to it, is going to push it to the right, and this far Q is also going to push it to the right, which means it's going to begin accelerating to the right. So the forces are imbalanced. You want to place it such that the sum of forces is 0. All right, let's try it here. Well, this positive 2Q, if you put it right here, is going to have a large force on it to the right due to this positive Q, but then a weak force to the left due to this other Q. So the net force is going to be to the right, so it's going to begin accelerating to the right. And the opposite is true over here. You push it over here, it's going to have a negative force to the left due to this positive Q. It's going to be repelled. And this positive Q over here is going to repel it to the right, a weak amount, which means it's going to begin accelerating to the left. The only place is to put it right here. Here at the positive, if you put the positive 2Q at 3, it's going to be repelled to the right, repelled to the left due to the positive Q here, and it's also going to be repelled to the right due to the positive Q on its left. And this force is going to be equal to the size of this force, and so you sum those forces in the x direction, and it's going to end up being 0, which is going to be equal to mass times acceleration. That means 0 divided by m is 0 acceleration. All right. So you're supposed to do this little quick thought experiment where you do hypothetical deductive reasoning. And so I want you to try that on the next couple slides. So let's try this again, but let's try it with negative Q's. And in this case, you just have a negative 1Q here, and here you have a negative 2Q. And you're going to place a positive Q on this number line, somewhere on this number line, such that it will not move. Where would you place it? Closest to 1, closest to 2, closest to 3, closest to 4, closest to 5. What do you think? Okay, well, hopefully you voted and you try to think about it like I did on the last problem. I like to start on these problems with the ends. I try to start here at 1, start at 5, and then start in the middle, and then hopefully that allows us to figure out what's going on. So if I place a positive Q right here, okay, it's going to be very attracted to the right due to this negative q, because it's very close, and distance is more important than the magnitude of charge. And then this negative 2q is also going to attract it to the right, but not as much because it's really far away. So essentially you're going to have two rightward attractive forces acting on our positive q, which means it's going to begin accelerating to the right. And that is also going to be the case over here. The positive q, if you place it right here at 5, is going to be very, very attracted to the left due to this negative 2q. It's actually going to have double the force of this guy. And it's going to actually have a somewhat weaker force to the left due to the other attractive force due to the negative 1q. So this is going to result with an acceleration to the right, to the left. Let's place the negative q right here. If you place the negative q, the positive q right here, well, it's going to be very attracted to the right, not as much as over here, and it's going to be somewhat attracted to the left. But there's definitely going to be an imbalance. Overall, the rightward force is going to be greater than the leftward force, and so it's going to begin accelerating to the right. So that's not true. And we could also imagine if we put the positive q here at 4, it's going to have the same size force as it did up here, but just to the right, and it's going to have a small force to the left, which is greater than this one because that's further away, but it's still going to have an imbalance to the right. So our best shot is put the positive q right here. It's going to be very attracted to the left, and it's going to be attracted to the right about the same amount, and those two forces are going to be in balance, or the closest to 2 is going to be the best shot. It won't be exactly on 2, but it's where our forces are the most balanced out of 1, 2, 3, 4, and 5. Okay? So how did you do on that? Were you able to reason appropriately through that? Thinking about the size of the charge and the distance, you have to take both of those two into account, just like we did that one earlier conceptual problem like this. It's kind of like this, actually. You have to consider both the charge and the distance as you're doing these little mini force diagrams and what-if scenarios and hypothetical deductive reasoning. Well, let's try another one. This is a cool problem too. Here you have a positive 2q, and here you have a negative 1q. Okay, and you're going to place a positive charge. Oh, I forgot to mention, I'm sorry. It doesn't matter actually if this is a positive 2q here, or a negative 1q here, or negative 2q, or any q. Any q that you put here will be in balance. And same thing with this. It doesn't matter what the charge is that you're putting here. It would be probably closest to balanced at 2, no matter what the charge was, negative 1,000,000 q or positive 1,000,000 q. It would still be imbalanced here at 2. All right, now let's move on. Here you have a positive 2q, here you have a negative 1q, and they're anchored in place. And let me just call this just a negative q. Blue is negative. All right, and it's anchored in place. Those two charges are anchored in place. You're going to place a positive q, or really you're going to place any q, somewhere on this number line, closest to one of these numbers, such that it will not move, meaning the forces will be balanced on it. There will be no acceleration vector. But we're just going to work with a positive q. So where would you place this positive q closest to, such that it will not move? 1, 2, 3, 4, or 5. Pause the video out and try doing the reasoning that we've just tried. Okay? All right, we're back. Well, again, I like to start on the outsides. Actually, I'm going to start here. I'm going to place a positive q right here. Okay? And when we do, it's going to have a very repulsive force away from this positive 2q. And it's going to have a somewhat attracted force to this negative q over here. But either way, the forces to the left are greater than the forces to the right. And when you have that kind of imbalance, that means you're going to have a net force to the left, which means you're going to have an acceleration to the left. Okay? Let's try placing it at 3. Let's place the positive Q here. Well, here at 3, it's going to have a force to the right, a very large force, not as large as this one, but it'll have a large force to the right, and it'll have a somewhat large, a force to the right as well. So this positive Q is going to repel it to the right, and this negative Q is going to attract it to the right, which is going to result in a net force to the right, which is going to give you an acceleration to the right. The same thing is going to actually happen here at 2. At 2, it's going to have a very large repulsive force to the right, which is the same size as this guy, and it's going to have an attractive force to the right that is greater than this guy but smaller than this. And so again, you're going to have a net force to the right, which is going to result with an acceleration. The same thing is going to happen here with that positive Q. Here, if you place it right here, it's going to have a large force to the right due to this negative Q, and then another force to the right due to the repulsion force of this 2Q, which again is going to result with an acceleration to the right. So 2, 3, and 4 are all going to result with an acceleration to the right. Our best shot is to place it right here. We place the positive Q here, it's going to be repelled away from this positive Q. This, it's going to be repelled away from this positive 2Q, and it's going to be attracted the same amount as this one due to the negative Q, which is going to be not exactly at this place is going to be the acceleration is 0, but close to this spot. Okay? And the important point of these 3 problems is how do you reason through weighing the Coulomb force to the amount of charge, but also to distance, and do that together at the same time. Okay? And you have to be able to do this. This is a really strong skill set. It'll really reduce the amount of work that you have to do on a lot of these problems when you're doing your homework and also in your tests. Okay? Well, here we have the lecture tutorials, and I want you to do this. I want you to try this out, and it's a lot like these problems right here, okay, where you have multiple charges acting on one charge. And so what you're supposed to do in this problem, it looks like you're supposed to do a diagram. So you're supposed to diagram the forces on each one of these charges and sum the forces on each one of these charges, given that this is a distance r, this is negative 2q, this is negative q, and this is negative 3q. Okay? And then it says they're going to ask you a lot of questions about that. Okay? So go ahead and try this out, and hopefully the exercises that we've done is going to help you out. But then, I guess in the end, you're just going to then be concentrating on this negative 2q charge. Okay, so this is going to help you out a lot, and it's going to be similar to D. So D is specifically going to help you out. Okay? So please work on your lecture tutorials, and I hope you had fun. This was Coulomb's force in 1 dimension. Okay? Bye.